Hello, and good morning again. Thank you for the introduction. First of all, my colleague Martin Kresta, the author of the paper, could not come today, so he asked me to take over his presentation. So my name is Filip Brtan. I'm an applications engineer on Semiconductor in vehicle networking business unit. And this is going to be something a little bit different from what we've heard so far. So no CAN-FD, at least in the next couple of minutes. What we prepared is a method that helps to decrease the power consumption and save the energy. So it's called ECU with emulated partial networking functionality. What does it mean? We try to develop and demonstrate, let's say, a new approach to selected wake-up, well-known selected wake-up functionality in order to improve the energy efficiency in CAN networking. Basically, it can be used in any networking, not just CAN networking, but let's say FlexRay. But I will focus on the CAN networking. In other words, we try to implement an alternative method similar to partial networking, which is based on the selected wake-up functionality, and all this is described in ISO 11898 part 6. Well, to be honest, this is not any revolutionary concept. And really, partial networking is still by far the most effective method. But it's, please take this more as an interesting research or case study, if you like. It's more about finding the limits in the possibilities in reducing the power consumption, and it helps to those who cannot implement this special partial networking CAN transceivers in their design. So I'm going to make a brief introduction about the partial and pretended networking. These are the points we started from. Then the main topic, or the main part, emulated partial networking. And I'll talk a bit about the ECU we prepared to be able to make some real tests. And finally, the results and all the comparison with the state-of-art solution. And at the end, I will conclude, of course. So, partial networking, heard about it. A lot has been said about partial networking. Motivation, the main idea is, of course, to decrease the overall battery current consumption, so reduce the fuel consumption together with carbon dioxide emissions. Partial networking defines a new so-called low power mode with selected wake-up functionality. And a new requirement is a special CAN transceiver that is able to handle all these things defined in ISO 11898 part 6. So while the standard CAN transceiver will interpret any frame or any communication on the bus as a wake-up event, this partial networking transceiver allows to stay in a low-power sleep mode or to stay asleep even if there is an ongoing communication on the bus. So it helps to increase the low power running time, and the consequences are quite clear, I believe. There is one disadvantage, let's say, it really requires a new special CAN transceiver which is able to handle this selected wake-up functionality. Then pretended networking, even if you don't have the special CAN transceiver, you are still able to decrease the current by methods of ECU degradation. This was described by the EEM group, or efficient energy management group, a special group within the AUTOSAR. And the main advantage is that you really don't need any hardware modifications. But on the other hand, it's not as effective, as efficient as the partial networking concept. The MCU can, for example, turn off the peripherals that are not needed, or it can decrease the number of tasks currently running in case you don't need it actually. So now the emulated partial networking. What we tried was to combine the advantages of both partial and pretended networking. Sorry, partial and pretended networking, and integrate the selected wake-up functionality without having the special CAN transceiver. So just only with a standard CAN transceiver plus the microcontroller. As you know, the main advantage of partial networking is, or the main benefit is this wake-up, selected wake-up functionality, while main advantage of pretended networking is no need of special hardware or the hardware modifications. So we combined it and we emulated the selected wake-up functionality with the software within the MCU or the microcontroller. As a result, we have something in between, not as efficient as partial networking, of course, but it's more effective or more efficient than the pretended networking, and it fills the gap somewhere in between the partial and pretended networking. One of the advantages, of course, or not of course, but is that we have a shorter wake-up time. This could be something as what we could call a benefit. And then, so to do so, we prepared such a ECU. It's based on a microcontroller and system basis chip. Both this microcontroller and system basis chip do provide several low power modes that is essential for preparing any ECU for low power applications. And we tried to, or we wanted to make this ECU, let's say, similar to the automotive ECU, the typically used automotive ECU. So we have microcontrollers, several peripherals, and the system basis chip. The system basis chip itself contains the CAN transceiver, and it provides low voltage power supply to the microcontroller. We used a standard 16-bit automotive microcontroller, and the SBC is one of the devices from our portfolio in Semiconductor. Now, what you see here is a block diagram of the ECU. Maybe here I would like to point out that we used a DC-DC converter instead of linear voltage regulator. There is, of course, an advantage of DC-DC converter. Is more efficient, and it helps in a way to improve the efficiency of the system. The system basis chips as such, especially if they contain or if they include the power management, they help naturally to increase the efficiency. But now we also have the DC-DC converter, so it's even better. Now the software architecture. What you see here is the architecture or the software stack. It was done to be similar to what AUTOSAR requires. So we have several blocks which are really based on AUTOSAR requirements, especially those in the microcontroller abstraction layers. And then the main block is the selected wake-up manager, which takes care of all the selected wake-up functionality. And that's, as I said, it's the main block. Well, I mentioned that it's based on or it follows the AUTOSAR requirements, not in all the details. There are some differences, some deviations from the AUTOSAR requirements, but it's mainly due to the fact that this is, let's say, an experiment. Of course, there is a possibility to implement all the ECU, including the selected wake-up manager, in a way that supports the AUTOSAR. Now, the MCU microcontroller power saving techniques. This is the main part which helped to improve the efficiency. The microcontroller contains or provides several low power modes, and the most important for us was the pseudo stop mode, where the oscillator is running, so it allows a very fast startup, but the clock is not distributed to the rest of the system, to the core of the microcontroller, and nor to the peripherals. It means there is a low, let's say, low current consumption. In this pseudo-stop mode, the PLL is also disabled, which helps to decrease the current consumption. And we have other modes as a wait mode, where we can enable several peripherals. It also supports fast startup, but the consumption is increased a bit. And finally, run mode, where we can have the PLL either disabled or enabled. And I'll explain what is happening during the startup. So, most of the time, if we want to run in a sleep mode or low power mode, we are in the pseudo stop mode, where, as I mentioned, almost everything is disabled, and the physical transceiver is in a low power standby mode. So it detects just wake ups, or basically it interprets any communication on the bus as a wake up. So when there is any communication, it reports this wake up to the microcontroller. It actually it writes an interrupt to the microcontroller, and the microcontroller switch from pseudo stop mode to the wait mode, where it enables CAN communication, and at the same time it switches the physical layer transceiver from the low power standby mode to the receive-only mode, where it can detect the communication and provide the data from the bus to the microcontroller. So the transition is very fast. That's a benefit. And now in a wait mode, we have enabled the receive-only functionality of the physical layer transceiver, and we are able to detect real frames on the bus. Now, if we detect the frame that is considered as a valid wake-up frame with a valid content and, let's say, the ID, the microcontroller can decide to wake up and proceed to the run mode. Now, I have an interesting figure or picture. This is a dynamic current consumption of the ECU. And you can see several, or to be specific, 4 frames. We sent remote wake-up frames that the microcontroller should detect as a wake-up frame. As you can see, the very first frame here, the very first frame is detected as a remote wake-up pattern. So there is low pulse on the RxD signal. Then the microcontroller is switched from pseudo-stop mode to the wait mode, and it enables the transceiver, or let's say the receiver, it switched the receiver to the receive-only mode, and the receiver starts reporting the data received from the bus to the microcontroller. Well, it takes, I will say, 2 frames to synchronize the internal communication controller, and then at the 4th frame, it is already able to decode the data to decide if the frame content is valid and if this is really a wake-up frame, and it will wake up what you can see here at this section. Well, the current peak which you see there is because we are starting the PLL inside the microcontroller, and it proceeds to normal mode when it can run on full performance. You can see that we are enough with 4 frames, so the startup is very, very fast, and at the time from the first wake-up pattern to the first effective instruction proceed by the microcontroller is something about 2 milliseconds. So it's quite fast. It's quite fast, and of course the current consumption is a bit increased in comparison to the requirements for the selected wake-up and the partial networking concept, but it's an option, as I said, to those who cannot implement these partial networking CAN transceivers. Well, there is another requirement for partial networking transceiver, and if there is no communication on the bus for more than specific time, it should switch back to the very low power sleep mode, and we also implement that. If the transceiver doesn't detect any communication on the bus within approximately 500 milliseconds, it will switch back to the low power mode when it can detect only the remote wake-up frame or remote wake-up pattern. So that's what we have. And now the comparison to the state of art or to requirements which is on the market. There is a OEM requirement spec, and especially or particularly to the partial networking, we have a requirement for 30 microamps in low power sleep mode with enabled partial networking functionality, while there is 500 microamps current consumption, the maximum, when there is an ongoing communication on the bus. What we achieved is a bit higher. It's 235 microamp for the low power sleep mode with partial networking enabled, and 3.5 or 3.4 milliamps to 4.2, depending if there is no communication. If there are frames that passes through the ID filter or not. So we have 3.4 milliamps or 4.2 milliamps at that mode. And finally, the normal mode, there is 12 milliamps, but this is outside of the requirements in the OEM requirement spec. So, of course, there is still a possibility to switch the transceiver or all the ECU to very low power mode without the partial networking functionality or partial networking-like functionality. And in that mode, we are able to achieve 60 microamps as an overall ECU, so the SBC plus microcontroller. Basically, the microcontroller is not powered at all. The voltage regulators are switched off, so this is just the current consumption of the SBC. Well, we have, of course, few advantages and few disadvantages with this method. And the main advantage is that you really don't need to have this special CAN transceiver, and there is reduced the overall wake-up time in comparison to the ISO 11898 requirement. Then, of course, you have your ECU, which is already produced and based on the standard CAN transceiver, which is basically usually robust in terms of EMC, and it's time proven, so you know what you have. And as I mentioned, this is a bit more effective in comparison to the pretended networking, which is also an option for those who cannot use these partial networking transceivers. Disadvantage, this approach is not defined in AUTOSAR. This is the main disadvantage. So as I said, it's just an experiment or a case study. And it's a bit platform to platform dependent. You really have to tailor the functionality or the software, the firmware to the microcontroller, to the platform you use. And finally, well, I think these are the main points. Then we have several deviations from the ISO 11898 part 6. So very first is, as I mentioned, the higher current consumption. Then there is one important deviation that there is a requirement in ISO 11898 part 6 that even the frames which contains the error signal in end of frame field, or let's say the error frames, should be considered as a valid remote wake-up frames. This is not the case with our concept, with our method. We tried. Another thing is that the timeout I mentioned, when there is no communication on the bus, is not fixed, but it vary from 256 to 512 milliseconds, depending on the precise point where we detect the very last frame. And the last deviation is that the FD error timeout is also not implemented. So it means the partial networking requires this function when there was an error frame. There should come at least one non-error frame within this timeout, and that's what we could not implement. Well, to conclude, I explained, or I mentioned the method we tried in our side. It provides another possibility to those who cannot implement the special partial networking CAN transceivers. We demonstrate this. We have a real hardware which we tested. We have some measurements which we can provide, and it was all about the implementation of the selected wake-up functionality within the MCU software. Well, as I mentioned, there are some limitations. It's not a perfect solution, but it's at least very interesting study or experiment. And there is of course possibility to further improvements or to further investigations in this way. So these are just the references I used, and that's all from my side. Thank you very much for your attention, and